Hi, Algebra 2 students. Sorry that I couldn't be there today, um, but thank you for loading up this video. We are going to go through the lesson sort of like we would have gone through it if I were there, do the warm-up, go over it, and then get into the actual skills of the day, and you should have plenty of time to practice. So the first thing is to just go over this warm-up. If you haven't finished the warm-up on your own yet, please go ahead and do that for some independent practice, but I'm going to go through and solve these just as some review. So if you've already finished, keep watching. For this first problem, again, my goal is just to isolate the variable. So when x equals something, I'm going to have to get rid of the things surrounding the x. That would be the coefficient of 3 as well as the constant of -10. And I'm going to remove those through inverse operations, in other words, opposite. So the opposite of what's already there. So here I have 3x minus 10. I'm going to start with an addition or subtraction. So I would start by adding 10 to both sides. And when I do that, right, -10 plus 10 is 0. So that cancels out and leaves me with 3x is equal to 24. And then since I have 3x, that's a multiplication. I can undo it with a division. So I divide both sides by 3, and x would be equal to 8. Okay. In my second problem, I am looking at this and I'm like, okay, inverse operations want to move things away from the x, yada, yada. But I may notice that there's actually an x on both sides of the equation. So if I want to end with x equals to some number, I'm actually going to need to start by just getting all the x's on one side of the equation. So I have 5x on the left side and 3x on the right side. What I'm going to do to get rid of the 3x and move it to the left side is I'm going to actually subtract 3x from both sides. I know you're like, that was a multiplication. Why are you subtracting? I'm treating this as an entire term that I want to move to the other side of the equal sign. So because of that, it is a positive term. There is a positive 3x there. If I take away a 3x, I subtract 3x, then that cancels out to 0. And so I can do the same thing on the other side to keep it balanced, leaving me with 2x minus 6 is equal to 2. Okay, and then it becomes a problem just like the last one where I have to deal with this constant first. So I add 6 to undo that subtraction. And then I have a multiplication to undo. And x is equal to 4. Okay. Moving on to number 3. Once again, I end up with x's on both sides of the equation. So I want to get all the x's on one side. Now I could move the -3x or the -x. What would probably be easier is to move the -3x, because if I were to add 3x to both sides, then I'll end up with a positive coefficient. You could add x to both sides, but I'm going to just add 3x to make my life a little simpler. Now, you'll notice you have -x plus 3x. Remember, if there's not a coefficient written in front of the x, there's a stand-in 1 there. So that's -1 plus 3. Since -1 plus 3 is 2, that leaves me with 2x. And then again, I can divide both sides by 2, and I have -2 equals x. It's totally fine that my x ended up on the right side of the equation here. Just notice that whenever I use inverse operations, I'm always focusing on removing the number that is surrounding the x. So in this instance, sometimes people will be tempted to divide by the -4, but since it's the 2 that I want to remove, right, I want to get the x by itself, I need to be dividing by 2 to actually cancel that out and leave me with my final answer. Last problem here, again, x is on both sides, so I'm going to move them. This time I'm going to move the -x because adding x to both sides, that'll keep my coefficients positive. So I'm going to add x here and add x here. Again, remember that that is one singular x. So 5x plus 1x is 6x. And then on the other side, it's all gone. If this ever happens, please, please, please don't just like drop the equal sign and just write 6x and be done with it. Okay. If everything on a side disappears, then you're left with nothing. That is represented mathematically with a 0. And that's very important because if you don't represent that with a 0 and you drop that equal sign, you're not going to be able to solve. In this case, you can solve, though, because I have now 6 times x. If I divide both sides by 6, x is equal to 0 divided by 6. 0 divided by anything is just 0. So x is equal to 0. Moving on to the next slide. Okay, so today We are going to work on solving exponential equations. Before we left for winter break, we looked at exponential equations for several weeks. We talked about writing exponential equations, graphing exponential equations. We did some applications with compounding interest. Now we are going to focus on actually solving exponential equations, so equations that have exponents with x in them. So in this case, we need to figure out how to solve. So this is the next page in your little notes packet for the day. So flip to the next page and take these notes. If two exponential expressions have the same base, so for instance, like 3 to some power and 3 to some power, then they also have to have the same exponent in order for the expressions to be equal to each other. Let's look at what this actually means in context. So I have some examples here where I have the same base. For instance, the base in example 1 is 2 on both sides of the equation because 2 is the thing that is being raised to an exponent. Now, in order for these expressions to actually be equal to each other, in order for each side to equal each other, the exponents have to be equal. Right? So this has to equal this. Okay? In this case, I see 2 to the 4 equal to 2 to the x. Well, I know that x has to be 4 because those expressions would only be equal if the exponents there are the same. Now, I can use the same principle to apply when the exponents are a little bit more complicated. For the second example, I have base of 3 on both sides of the equal sign. I know that this exponent has to be the same as this exponent. Well, that doesn't actually tell me right away what the exponents would have to be, but I can figure it out because if those two exponents have to be the same, I can set them as equal to each other, and then I have an equation that I can solve just like we were practicing in the warm-up. So I'm going to go ahead and solve this equation. I'm going to start by moving the x to the right side. Again, you could subtract 4x from both sides, but to keep coefficients positive, I like to always subtract the smaller number of x's. So that would leave me with 0 is equal to 3x minus 3. And then I can add 3 to both sides. 3 is equal to 3x. And then again, because there's a multiplication, I'm going to divide by 3. And then I'll find that x is actually just equal to 1. So now that we've learned this, you have some examples that you can practice with. So it's going to be the same concept over and over. You'll notice in all these examples, you're given two equivalent bases. So for instance, 7 and 7. So you know that you have to set the exponents equal to each other. So do that with this first one and then continue on and do it with all the other ones. While you do this, I want you to pause the video and you're actually going to come back to the video and unpause it once you're done this in order to check your work and learn the next skill. Okay, so if you're still listening, that means you should have practiced these on your own. We're going to go ahead and go over it. In this first case, the exponents were a little bit simpler, so I just saw x has to be equal to 6. In the other examples, I'm setting exponents equal to each other. When I do that, I'm then going to have to solve an equation to actually figure out what x is equal to. So I set this exponent equal to this exponent, and then I was able to solve and find x is equal to 7. I'm following that same process for all these other problems. Again, just setting the exponents equal to each other. So go ahead, check your work. If you need to look a little bit longer or have any more questions, you can obviously pause this video again. But yeah, once you are good with this, we are going to move on to the next skill. So we just talked about how to solve exponential equations if they have the same base as each other, but now what if they have different bases? Okay, if you have two exponential expressions with different bases, but they're equal to each other, so for instance, something like example 1, 4 to the x, one of the bases is 4, the other base is 2. You want to start by rewriting the expressions with the same base, and then you can solve using the same process we just learned. How am I going to do this? Well, I do this by basically figuring out how to rewrite the larger base as the smaller base to some exponent. So here we have a base of 4 and 2. So I'm going to leave the base of 2 as is because that's the smaller one. And I want to figure out how I can rewrite 4 with a base of 2. So I'm asking myself 2 to what power gives me 4? Now, if you know your exponents well, especially with the ones that are smaller numbers, it's maybe easier to figure out. If you need to do a little guess and check, you can use your calculator. That's fine. But in this case, I know that 4 happens to be 2 to the second power. Again, if you need to play around your calculator, you say, what is 2 to the first power? What is 2 to the second power? What is 2 to the third power? Until you find what's equal to 4. That's fine. So I can rewrite 4 as 2 squared. In other words, 2 to the second power. And then that's the same as writing 2 squared to the x power. I put 2 squared in parentheses because that whole thing is just representing the 4. It replaces the 4. And I want to show that x is the exponent for that entire expression. And that equals 2 to the x plus 3. At this point, I need to use a little bit of exponent laws, which we learned long before break, but it is going to come back. It's the same exponent law that we're going to be using over and over, though, because it's going to be the same process every time. And we're remembering that if I have a power that's being raised to another power, so here I have like 2 exponents, one exponent is being raised to another exponent, and the way I simplify that is to multiply those 2 exponents together. So I can write this with just a base of 2, and then with the power being 2x, because it's 2 times x. So I'm left with 2 to the 2x is equal to 2 to the x plus 3. And then once I've rewritten it like this, you can see that I have an equation just like the ones we practiced on the last page. Okay, and we can solve it as such. So I'm just going to set those 2 exponents equal to each other. So I would say that 2x has to be equal to x plus 3. And then I can solve from there. Looking at example number 2, we have 81 is equal to 3x. Interestingly, the left side isn't even an exponential expression right now, but I can still rewrite it as one because I do want both sides of my equation to have the same base. So I want to figure out how to write 81 as 3 to some power. Again, if it's going to be a little bit bigger one. So if you need to use your calculator to practice what is 3 to the first power, well, 3 to the first power obviously is just 3. What is 3 to the second power? What is 3 to the third power? You'll find that if you do 3 to the fourth power, then that would give you 81. So I can replace the 81 with 3 to the fourth power. Okay, and then 3 to the fourth power is equal to 3 to the x. So again, since those exponents have to be equal, I know that 4 is equal to x, and I already know what x is. Moving on to example 3 here. I have 9 to the 2x plus 5 equals 3 cubed. Again, I want to rewrite the 9 with a base of 3. I'm always going to rewrite with the base of the smaller number. So 9 is the same as 3 to the second power. So I'll say 3 squared to the 2x plus 5 power equals 3 to the third. And remember, I'm just multiplying those 2 powers together because one power is being raised to the next power. So in reality, I have 3 to the 2 times 2x plus 5. Now when I do this, I'm going to have to write that 2x plus 5 in parentheses because I want to multiply the 2 times that entire thing. So whenever you are doing this, make sure that when you multiply, you're multiplying the entire thing. So if one of the exponents has multiple terms, you do need to put it in parentheses. So here, I'm going to have to actually distribute the 2 to both those terms. Remember, if you have parentheses, you have to distribute, meaning multiply in that term on the outside. So when I'm rewriting this again, I'll be multiplying 2 times 2x to give me 4x. And 2 times 5 to give me 10. Okay, and that equals 3 to the third power. And then again, I'm going to set my exponents equal to each other now that they're fully simplified and solve. So I'm trying to isolate x, so I'll get rid of this 10. It's a positive number, so I will subtract to do the opposite. 4x equals to negative 7, and then I can divide both sides by 4. And I'm just going to leave this in fraction form. If you were to actually divide that out, it would come out to negative 1.75. But I'm fine with us just leaving it as a fraction. I feel like that's not right. 3 squared. No, it is. Okay. Okay. Now looking at the last example, you'll notice something a little bit different. We got a fraction on one side. And this is a little bit of a challenge problem, but you may remember when we did exponent laws, we talked about how a negative exponent represents a fraction. It represents switching the location of the numerator and denominator. So in this case, I have a base of 7 on one side. If I want to write this 1/7 as a base of 7, basically that means I want to move the 7 from the denominator into the numerator. In order to flip that, I just have to write this as a negative exponent. So I can actually say, instead of 1/7, I could say 7 to the negative 1. And then I see that these two already have the same base, so I can set the exponents equal to each other. And then I can solve. Be really careful when you're adding and subtracting negatives. If you need to double check your work in a calculator, that's fine. And x would be equal to negative 2. So now that you have all these, please make sure you have everything copied down correctly in your notes. And then work on the examples below this. And then again, if you can pause the video right now, come back to the video again when you are finished with this to go ahead and check your work. Okay, so to check our work, again, I'm just constantly rewriting with that smaller base. You'll notice here that I sort of skipped a step. You don't really need to always write every step, but when I rewrote 216, instead of writing it as 6 to the third to the 3, instead of writing it as 6 to the third to the x minus 3, I knew that my exponent laws are always going to work out, so I have to multiply the exponents. So if you want to use a shorthand and just be multiplying those two right away, that's fine. If it helps you to rewrite it like we did earlier, that's okay as well. And same process, following it for the rest of the problems. That one again, it's the fraction, so whenever you see that, you'd have a negative exponent. So if you need more time to look at this, that is fine. Make sure you have all these correct. You're correcting any mistakes before you move on. There's one more page to complete if you have time before the end of class, and there's also I don't know. I think there's going to be a Kahoot or something linked on the Canvas page, but I could be wrong about that. So just worry about finishing as much of this packet as you can get through. And yeah, thanks for listening.